Okay, so great. Yeah, well, okay, oh, so a couple things. I apologize, I had not posted the questions to go along with the article until early this morning or late last night. Oh, yes, slides put on CCLE. Yes, I can do that. Again, these will just be a draft of the slides. I often have to catch some mistakes and typos as I go along. So, so keep in mind this is just a draft. Okay, I hope you had a chance to read the journal article. I think it's interesting, and I finally posted some questions to go alongside of them. I got some 10 questions right here, and you'll go over the answers in your discussion section today. So there's one question that question 8. You know, we haven't covered this directly in class. It's a confidence interval for difference. We'll cover that on Monday, actually. But I think because you will have seen confidence intervals by, you know, you've already seen some confidence intervals. I think kind of the expansion will make sense. But anyway, make sure you read the article, and you'll go over that in class. And then I'm still writing my last quiz, so there's still a quiz 4 that's going to go on Gradescope, and I will get that posted a couple hours after class finishes. So so I'll get that posted, and that'll be due, you know, as normal on Friday. Okay, so today we are going to cover inference for numeric variables. So we will start chapter 9, and we'll cover a good deal of chapter 9. I don't think I'll be able to cover all of chapter 9 today, and so the rest will be left for Monday. And yeah, and then we'll wrap up there. Next Wednesday we'll spend some time doing review for the final exam, and then the final exam will be next Friday. Okay, so whoops, I should get rid of that slide. Okay, so what we're covering today is we're looking at numeric variables. Okay, so up until so chapters 7 and 8 were dealing with categorical variables, and we were dealing with proportions. It was things like, you know, what's the proportion of, you know, the times the coin flip landed heads, right? The outcome of the coin flip is categorical. It landed heads or it landed tails. Or it might be, you know, what's the proportion of people who have this political opinion, and it's going to say, you know, people have this opinion or this opinion or this opinion. You know, what's the proportion of people who got better with the medicine? And those were all kind of categorical outcomes. They got better or they didn't. And today we want to introduce methods that will allow us to take a look at numeric variables, right? So we might have a variable such as, you know, are things associated with someone's blood pressure, okay? And blood pressure, you know, is measured in millimeters of mercury, and you know, and it's a number. So, you know, somebody might have a blood pressure of, you know, we'll go with like the systolic blood pressure. So that's the first number in the blood pressure reading. So it might be something like, you know, one person has a blood pressure of 120 and somebody else has a blood pressure of 110 and someone has a blood pressure of 135 or something like that. And those are numeric values. And we might be interested, you know, in a sample, and you know, just like everything else, when you take a sample, the sample statistic will vary from sample to sample. So if you have one sample and you take the mean of one sample, and then you take another sample and you calculate the mean of that sample, even if they come from the same population, we don't expect those two samples to be exactly the same, right? And so whenever you take a sample from the population, we expect that sample's mean to be close to, but not exactly equal to the population mean, okay? So just like when we were dealing with proportions, when you take a sample, we expect the sample proportion to be close to, but not exactly equal to the population proportion. Same idea applies to the mean. If you take a sample's mean, you expect the mean of the sample to be close to, but not exactly equal to the population mean, okay? And so we're going to look at the sampling distribution of the sample mean, okay? So in chapter 7, we had the sampling distribution of the sample proportion. And today we will look at the sampling distribution of the sample mean, okay? And some sample means will be more likely than others, all right? So to kind of illustrate this, I'm going to run this little website, okay? Pull it up right here. And the idea here is, forgive my drawing. We got a question. Is this what people are talking about when they say means testing? Ooh, I am not 100% familiar with that terminology, means testing. But I imagine it's related to doing a hypothesis test with the means, which we will cover later today, okay? So hypothesis test with means might be what they're referring to when they say means testing. Okay, so the idea here is you've got a big population, and the population is too big for us to observe directly. And so what we will do is we just take a random sample, right? We take a random sample of size n, and we calculate the mean of that sample. Sorry, I used the letter y bar instead of x bar. They're the same thing, the mean of the sample, okay? And then I can take another random sample, same sample size, but because it's random, I'm gonna get a slightly different sample mean. I'm gonna get a slightly different y bar. Same thing, sample 3, another same n, but a different y bar. Sample 4, same n, and a different y bar. And I just do this over and over and over and over and over again, okay? We're gonna repeat this thousands of times. We're gonna keep track of all the different y bars that we observe. And this will give us a sense of the distribution that we see, okay? So I'm gonna go ahead and do this on this website, okay? So this is, let me see if I can zoom in here. Okay, so this up here represents our population, okay? So this is the population, and I know I said we can't observe it directly, but you know, for the sake of the simulation and for educational teaching purposes, we know what the population looks like, okay? And so the population looks like this. We've got a normal distribution. The mean of the population is 16, and the standard deviation is 5, okay? And what I'm gonna do is I'm gonna take, say, samples, we'll start off with samples of 2, okay? And I'm just gonna take a sample of 2, okay? I draw 2 values, and this one came from right here, this one came from right here, okay? And the mean of these 2 values is in between them, and that's right here. And so what we're gonna do, every time I click this button, it's gonna draw a sample of 2, it's gonna calculate the mean of these 2 values and drop basically a little block to kind of build up a distribution here. Okay, do this again. Take 2 values from this population. These are the 2 values. The mean of these 2 values is right there, and it drops this down. two more values just by random chance. They happen to be close to each other. The mean of these two values is here, and it drops down, okay? I'll go ahead and do that. These ones happen to be far apart, but their mean happens to end up in the middle. Here's two more values, okay? And I can just keep clicking this, and every single time I click this, are you guys able to see this clearly? We're on Zoom, and I don't know how much latency there is. Okay, all right, you guys are able to see this. Okay, so I click this, and it's drawing two values out of the population, and it takes the mean and it drops it down. Okay. Oh, look at that, we got a value, extreme value. So anyway, I'm just doing this, and we do this over and over and over again. Okay, so instead of having to just click this one at a time, I can just kind of click, I can say do 5 at a time, and it's going to kind of skip this part right here, and it's just going to add 5 chunks to the thing, okay? And so, and then instead of having to just click 5 a whole bunch of times, I'm going to just go ahead and click 10,000, okay? And look at that, okay? This is the resulting distribution, all right? And so what do we notice? So here I've taken apparently 170,000 samples, over 170,000 samples of 2 at a time, okay? And this is the distribution, and what does it look like? It looks a lot like this, except a little bit narrower, right? The mean of this distribution is 16, and what do we notice? The standard deviation of the population is 5, and the standard deviation of my sampling distribution, these are all the different sample means that I've got, the standard deviation of that is a little bit smaller, okay? And the shape of this thing is normal, okay? What do you think would happen if I take, instead of samples of size 2, what would happen if I take samples of size 5? So I'm going to go ahead and animate this. So here's one sample of 5. I take 1, 2, 3, 4, 5. And what's the mean of all 5 of these numbers? It's right there. Here, we'll take another sample of 5. 1, 2, 3, 4, 5. What's the mean of these 5 numbers? It goes right there. We'll take another sample of 5. 1, 2, 3, 4, 5. What's the mean of those 5 numbers? Drops down right there, okay? So if I do this a whole bunch of times, what do you think this distribution will look like? Hey, feel free to unmute yourself and just say something. There's 40 of you here. Okay, normal, yeah. Okay, we'll expect it to be normal. What do you think the spread will be, okay? Does it get narrower? Yeah, okay, so a student asks, does it get narrower? And indeed, it will. Okay, let's go ahead and take a look, okay? So here, again, I can just click 5 at a time, and it's doing 5 samples at a time. And we're already getting a sense. I'm gonna go ahead and click the 10,000. So here's after 130,000. This is what the sampling distribution looks like, okay? So the mean, again, is like right around the population mean. The population mean is 16. We're getting 15.99. I bet if I do like another, no, maybe not, but we're getting something very, very close to 16, 15.99, okay? And the standard deviation is 2.23. If you remember, for sample sizes of 2, my standard deviation was around 3.54. For sample sizes of 5, my standard deviation is 2.24, okay? Yeah, so the distribution does get narrow. It still remains normal, but the distribution does get narrower, right? And if I increase to sample size 10, and again, the idea here is we're going to draw a sample of 10 values, so 9, 10, and we take the mean of all 10 values, and it drops down right here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values, 10 random values. What's the mean of all 10 of those values? It's right there. We'll take another sample of 10 values. Okay, what's the mean of those 10 values? And it goes right there. I'll just do this one more time. A sample of 10 values. What's the mean of those 10 values? And it drops down right there. Okay, and if I just go ahead and jump to 100,000 of these things, we get a mean of 16, and the standard deviation is even narrower at 1.58. Okay, and if I jump all the way up to sample sizes of 25, okay, the sample is huge. We've got 25 numbers to sample, and it's going to take us a little while to animate this. Okay, and what's the mean of all 25 of these values? It's right there. Okay, and if I go ahead and I just click 100,000, this is what we get, and we get a standard deviation of 1. Okay, so sample size of 2 has this. Sample size of 5 looks like this. Sample sizes of 10, it gets narrower. And sample sizes of 16 get even narrower. And if I jump up to sample sizes of 25, it gets even narrower. Okay, so intuitively, why is our sampling distribution getting more and more narrow? Okay, well, what we're plotting, okay, again, with a sample of, just so we don't tire ourselves out, with a sample of 10, okay, remember what we're plotting down here is the mean of all 10 values, okay? And so with 10 values, here's a sample where, you know, all 10 values kind of came from fairly the middle-ish area of the population, right? Here, I got one value that's fairly extremely high, and I got one value that's fairly extremely low. But again, when you take the average of all of these numbers, even though you get an extreme value over here or an extreme value over here, they kind of balance each other out when you take 10 values, and the mean of those 10 values still ends up being very close to the middle. Here's another sample of 10, and I happen to get a couple values that are kind of extremely low, right? And I didn't, just by chance, I didn't get any values on the extremely high side. And so the average of those 10 numbers is down here, okay? And again, here's another sample of 10. And by random chance, most of them are kind of in the middle-ish area, and the average ends up over here. When you take samples of size 2, you can get values down here, values up there. And let me just do this a few more times. With samples of only 2, it's not going to be that strange of an occurrence for just both values to end up from the high side or both values to end up from the low side. Okay, so okay, and you know, when you take large samples, you're more likely to get more values that are kind of closer to the middle that kind of balance things out. Okay, so here's one where we got an extremely low value and one in the middle, and so the value ended up kind of dropping towards the end and stuff. Okay, so with samples of size 2, you might get values way down here, and you end up with more spread. Okay, so as you take larger samples, it becomes more and more unusual for all of your values to end up on the high side or all of your values to end up on the low side. So it's a rare occurrence for the average of all 10 values to be you know, even like moderately high or moderately low. Whereas with samples of only 2, it's not going to be too weird for both values to be large or both values to be small. And with samples of size 25, it becomes even more pointed in that for you to get a large value over here, for the average to be large, all 25 values are you need to have a whole bunch of values that are extremely high, okay? If you get one value that's low, then you need to have even more values that kind of balance it out to be very high. And so that becomes a rare circumstance. So that's what happens when you have a population that looks normal. And I think I've kind of plotted this, and what we see is here's the population that's normal, and as the sample size increases from 2 to 5 to 10, I guess I didn't need to rewrite these numbers, they show up right here, we could see that the standard deviation shrinks, okay? They all kind of retain this shape of being normal, but the sampling distribution gets more narrow, okay? I want to, so this thing also allows you to have a distribution that's, say, uniform, okay? And so a uniform distribution says that all values from 0 to 32 are equally likely, okay? So with the normal distribution, whenever you take, you know, if I take values of, say, like 10 or something, most of the values will come kind of from this middle-ish region, and we very rarely get values up at 32 or values down at 0, okay? So if I take another sample of 10, we don't get any values way up here or way down here, okay? Whereas if I have a uniform distribution, okay, all the values are equally likely. So I'm gonna get some values way up at 32. I'm just as equally likely to get some values all the way down at 0, just by random chance I'm not. But, you know, we saw some time 32s getting drawn. We'll see, you know, here's some values, 0s and 1s and stuff like that getting drawn, okay? Here a 0 got drawn, which, you know, didn't happen when we had a normal distribution, okay? So with that in mind, any idea what would happen if I take samples of 2 and we create a sampling distribution? So again, I'm going to just draw 2 numbers from 0 to 32. All of these numbers are equally likely. We're going to take the average of them and plot it down, okay? So here I happen to get 2 values that are down here, which is not unusual because all the values from 0 to 32 are equally likely. So what do you think will happen? So I don't want to keep clicking this over and over and over again. So I can start adding 5 at a time. Okay. So here's kind of a preview of what it looks like after, say, all right, so here's a preview of after 100 samples of size 2. 100 samples of size 2. Okay, so someone says, maybe it's starting to look normal. Okay, well, I think everybody will be surprised at what happens, because I'm going to go ahead and click 10,000 and then 100,000. And what do we get? We get something, this is like a triangle. This is like a pyramid, okay? And I think that's surprising, right? Like, I don't, probably we were not expecting it to look like this, but that's what ends up happening, okay? And if we think about it, okay, because remember, we're plotting the mean here. So there is only one way to get 32, okay? You have to, for the average to be 32, both numbers have to be 32, okay? And then there's 2 ways to get an average of 31.5. One can be 31, and then the other can be 32. Or you can get 32 and 31. And then there would be 3 ways to get an average of, or there's, yeah, 3 ways to get an average of 31. You can get 30 and 32, 30 and 32, 32 and 30, or 31 and 31. Okay, those are the 3 ways to get 31, an average of 31. Okay, and then there's 4 ways to get an average of 29.5. You can get, what are they? 29 and, wait, what? 30.5, an average of 30.5 will be 29 and 32, 32 and 29, 30 and 31, and 31 and 30, okay? And it's kind of a little bit like dice in that there's actually just one more way than the kind of the adjacent thing. So like if you think of dice, you know, there's 6 ways to roll a 7, and there's 5 ways to roll a 6, and there's 4 ways to roll a 5, and 3 ways to roll a 4, and 2 ways to roll a 3, and 1 way to roll a 2, and things like that. And so it's kind of like rolling a die, except would be a 32-sided die, which would make for interesting Dungeons and Dragons games and stuff. But this is what we have. So with a sample of size of 2, you get a triangle. Now, this app only allows me to go with samples of 2 or 5, and I just kind of want to show you what happens when you have samples of size 3. And so to kind of code this up, I wrote a little bit of code here. Okay, and so here we're going to have, so let me just show you. So I think you guys did this in lab 4 or something similar, right? Or am I imagining this? Where you generated sampling distributions, and I don't know what code you guys use exactly in your lab 4, but here I've got a population, and these are the numbers 0 through 32, and what I'm going to do is I'm going to use sample to draw from that population, and I'm going to take samples of size 2. I'm going to set n as 2, samples of size 2. We're going to calculate the mean of each sample, and I'm going to store those away. Okay, and so I'm going to go ahead and run this, and when I do that, we can see we get the triangle distribution that we had. Okay, all right, and so I'm going to just increase this to samples of size 3, and I want you to see what the distribution. Here, let me, this one. Okay, sampling distribution with n equal to 3. Okay. Here, actually, let me go back and do. We'll start off with n equal to 2. All right, so that's n equal to 2. Here's n equal to 3. Here is n equal to 4. So again, each time I'm generating a sampling distribution. I'm saying take a sample from the population. Each sample you take has size n, and we're sampling with replacement because I only have 33 numbers in the population. And we're going to calculate the mean of whatever sample I've drawn, and I'm storing it away in the this vector sample means. Okay, so here this is a sampling distribution with n equal to 4. We'll do a sampling distribution with n equal to n equal to 4. Here it is with n equal to 5. And we'll do 6 and 7. And what do we notice happening? Okay, so keep in mind, my population is this uniform distribution. Okay, so I didn't create a plot in R of this, but my population is uniform. All numbers from 0 to 32 are equally likely. And what we notice is that, yeah, when we take samples with n equal to 2, we get that triangle distribution just like we did here. And if I jump up to n equal to 5, we get this thing that looks a lot like the normal distribution, which is what we see here. I've got n equal to 2, n equal to 3, 4, and 5. So this result should look a lot like this result here. And I would say it does, okay? And as n increases, here it is with 6, 7, 8, 9, 10, okay? We get, where we go? N equal to 10, okay? And this result should look similar, which I think they do. as we increase our sample size, and then I can do increase my sample size. Here it is with n equal to 15 and n equal to 20 and whatnot. Our distribution we see starts to look very normal, and the spread gets narrower and narrower. Okay, and this would be confirmed here. If I go from 10 or up to 16, up to 20, and up to 25, we can see each of these things. Here my standard, with n equals 25, my standard deviation is 1.9. And as I decrease my sample size, the standard deviation gets wider, right? Or conversely, as I increase my sample size, the standard deviation changes as well. Is that okay? So, I think this is interesting. Okay, it's interesting that with a uniform distribution, when you take samples of size 2, you get this pyramid thing, very not normal. And then, so here it is with 2, we get a triangle, okay? With 3, we get something that kind of resembles normal, but definitely if we if we did an analysis on these things, this would not be a normal distribution. It's the hill is way too fat to be considered a normal distribution. A normal distribution has a very particular shape, and this is it would be unimodal and symmetric, but kind of the slope of this this hill and stuff it does not quite fit the normal distribution. But as I bump up, bump up my sample size n, I think people would start to say, okay, this is starting to look like the normal distribution. And definitely by the time we get to 10, kind of the angle of climbing and going down the hill here is very much like the normal distribution. So that's kind of an interesting thing, okay? You can do other things, so you can actually change. So here, I want to, oops. So I'm going to make this silly population, okay? All right, so in this population can only produce values like 0, 1, 2, 3, 4, 5, or 26, 27, or 27, 28, 29, 30, 31, 32. Okay, so it can only produce values on the low end or the high end, and it will never produce values like 16 or 17 or even 10 or things like that. Okay, and so let me just kind of animate what this looks like. Okay, so here I got one value. Let me clear this lower ones. So here both values came from the top side. Here one value came from the top and one from the bottom. One from the top and one from the bottom. Both from the top. I want to get one. I want to get one where both of them come from the lower side. Just by random chance, we're not getting one of those things. Oh, you're killing me, random generator. Okay, finally, thank you. Sometimes you can get both values to come from here. Okay, so if I do this, okay, and there you go again. If I do this over and over and over again, what do you think the resulting distribution of sample means will look like? Like, will it even look like anything? 3 separate normal curves? That's actually a good, very good guess. So what we're actually going to get is we're going to get 3 separate triangles, 3 pyramids. Okay, we're going to get 3 pyramids. Okay, where the middle pyramid is taller. Okay, because here you get basically a pyramid where both values came from the low end. You get a pyramid for when both values came from the top side, and then you get a pyramid where one came from the bottom and one came from the top, and then that combines with the pyramid where the first one came from the top and the second one came from the bottom. And so that this middle pyramid is twice as tall, okay? And I can simulate this as well in R. I'm going to change my population to be the values 0 through 5 and 27 through 32. And we'll go ahead and clear all of these out. And we'll start off with samples of size 2. And here it is. We get my kind of my 3 pyramids as well. Okay. Maybe I should see if this improves anything. No, it doesn't. Okay. Okay, so let me just show you. Okay. So samples of size 3. What do you think we'll get? If I take samples of size 3, I'm going to end up getting 4 pyramids. Okay, so let me do samples of size 2 again. Sorry, just for the sake of illustrating this. Okay, so samples of size 2. Here it is with samples of size 3. Okay, samples of size 3, I end up getting 4 pyramids. Okay, and the situations are all 3 came from the lower side. 2 came from the lower and 1 came from the high. 1 came from the lower and 2 came from the high, and all 3 came from the high side. Okay. With samples of size 4, I get 5 pyramids. Okay, so this is kind of, so you can kind of think of it as like having teams, right? And you can go, 4, 0, 1, 3, 3, 1, 2, 2, or I'm sorry, 4, 0, 1, 3, 2, 2, 3, 1, and I'm getting all of these mixed up, but all 4 came from the lower side, 3 came from the lower, and 1 came from the upper side. 2 came from the lower, and 2 came from the upper. 1 came from the lower, and 3 came from the upper, and all 4 came from the upper side. Okay, and so you end up getting more pyramids. And I'm going to just keep bumping up sample size equal to n equal to 4, and we get this. With n equal to 6, we get that. Let's do 7, 8, and 9. So these are the sampling distributions. N equal to 10, 11, 12. Okay, I think you are starting to see where it is headed, okay? And so by around n equal to 15, n equal to 16, it's not, we still have this weird jagged pointiness, okay? But we're starting to get a shape that is a little bit more and more smoother and normalish looking, okay? As I bump this up, okay? Okay, by the time I get to n equals to 23, this thing looks quite normal-ish, I would say. N equal to 24, n equal to 25, okay? And then I'm going to just go ahead and jump up to like n equal to 30, n equal to 35, n equal to 40. And so anyway, this is what the distribution looks like, okay? So this is, again, the plot of all the different sample means that we get. As I kind of just bump up my ends, the resulting sampling distribution ends up looking normal, okay? So here's I kind of put in the summary of all of these pictures in here, okay? And so, here I have this dichotomous population where it can only produce low values or high values, and we see this you know, we get these different triangles, these different pyramids, and as the sample size increases, it looks normal. Okay, um, and this was just kind of a simulation, but you know, mathematically we can also prove that that this phenomenon actually exists and happens. Now, we're not going to bother with the theoretic math in our class. If you do major in statistics, you will have to take a theoretic statistics course. It's actually a lot of fun and really fascinating. If you appreciate of like, if you enjoy like these, you know, beauty of math type of things, it is kind of a neat thing. But beyond the scope of our course. But anyway, all to say is that the shape of the sampling distribution becomes normal as long as the sample size is big enough, right? So, you know, when we had sample sizes of whatever down here, nobody would say this is a normal distribution, right? Sample size of 9, it's not normal, but you bump up to sample sizes of, you know, 40, 50, as long as the sample size is big enough, this looks a lot like the normal distribution, okay? And there were a couple other things that we saw, right? The mean of the sampling distribution is equal to the population mean. And we also saw this. The standard deviation of the sampling distribution, that is the standard error, shrinks as the sample size increases, okay? As our sample size got bigger and bigger and bigger, the width of the sampling distribution got narrower and narrower, okay? And again, we're not going to bother trying to prove this. I'm just going to tell you that the standard error is found by doing sigma, that's the population standard deviation divided by the square root of n, okay? So, you know, n is in the denominator, so as n gets bigger, the standard error decreases, okay? And so we can say x bar comes from a normal distribution with mean mu and standard error equal to sigma over the square root of n, okay? And so, that's the result of the central limit theorem. So we saw the central limit theorem apply to proportions, and there were a few conditions that you know, had to be true before we applied the central limit theorem. And likewise, the same kind of thing applies here when we're dealing with sampling distributions of sample means. Okay, so so pretty much the conditions are the same. You got the random and independent sample has to have a large sample, and you have to have a big population. So the sample needs to be selected randomly, and individuals need to be independent of each other. That condition remains the same. This big population, if we're sampling without replacement, the population needs to be at least 10 times bigger than the sample. That condition is also the same as what we had when we were dealing with proportions. And then the only thing that really changes is the large sample condition, okay? The idea that the sample has to be large enough, that remains the same, but how do we check that? You know, with proportions, we said n times p has to be bigger than 10, and n times 1 minus p also has to be bigger than 10. Here, it's a little bit more vague. If the population is normal, any size is large enough. And we kind of saw that here. You know, when the population was normal, even though I took samples of only size 2, the resulting distribution looks normal. Okay, with the population being normal, samples of size 2, that was big enough for this thing to have a normal distribution. Okay, when you have something that's not normal, you know, a sample of size 2 is not big enough. Okay, so if the population is not normal, larger samples are required. Okay. The rule of thumb is, in general, a size of 25 is considered large enough for most cases, but in extremely skewed distributions, a sample size greater than 25 might be required. You know, in most cases, samples of size 25 are big enough. And generally, the closer, the more unimodal and symmetric the population is. Okay, so if the population is unimodal and symmetric, even if it's not perfectly normal, so you might have something that looks like this. This is not a normal distribution, but it is unimodal and symmetric. Okay, samples of size 2, maybe this is not perfectly normal, but probably by the time we get samples of size 5, this would be normal enough, okay? If I fit a normal curve over it. So pretty much the same conditions, it's just on a practical level, checking the large sample condition is a tiny bit different, okay? We don't have a p to multiply. So we just, the rule of thumb, if it's 25, that's a big enough sample, okay? That's for most circumstances. Oh yeah, let me give you your first viewing quiz answer. First quiz answer is C as in cat. C as in cat for your first quiz answer, okay? C as in cat. Okay, so that is sampling distributions for this. Oh yeah, I have an example problem here. Okay, so we'll say the pulse rates of adult women in the United States are approximately normally distributed with a mean of 74 beats per minute and a standard deviation of 13 beats per minute, okay? If we select a random sample of 36 women, what is the probability that the mean pulse rate of this entire sample is under 71 beats per minute? Okay. So how do we do this? Well, our sample size is 36. The mean of the population is 74. And the standard deviation is 13. I forgot to include that in there. But I mean, it's in the text of the problem. Okay. The mean is 74. The standard deviation is 13. And we want to know what's the probability that the mean the mean of the sample is under 71, okay? So from the central limit, we can apply the central limit theorem because our sample is big enough. We have a sample of size 36, which is bigger than 25, but the reality is the population is normal, so any sample size is big enough, okay? Random and independent, it says the sample is a random sample, so the sample of 36 women is randomly selected, so that's met. And the big population, the population would be all adult women in the United States, which is much bigger than 10 times 36. So we can apply the central limit theorem. So from the central limit theorem, we know that x bar will come from a normal distribution where the mean is equal to the population mean of 74, and the standard deviation is going to be 13 divided by the square root of n, 13 over the square root of 36, which gives me around 2.167. And I would calculate a z-score. I would do x minus the mean divided by the standard error. 71 minus 74 over 2.167, I get negative 1.38. I would go to my z table, and we look up what's the probability that z is less than negative 1.38. And we get around 8%, okay? And so we say there's about an 8% probability that the mean pulse rate of this sample will be 71 or lower. Okay. Is that feeling all right? Because this is going to form the kind of the foundation for, you know, what the rest of what we do in the chapter. Okay. Sorry, you didn't catch the first quiz answer. Okay, first quiz answer is C. C as in cat. That was the first quiz answer. All right. Well, why don't we take a short 5-minute break here, and we'll come back and we'll finish the we'll finish today's lecture in 5 minutes. So we'll take a 5-minute break. Okay, so now that we said x bar comes from a normal distribution, we can develop a confidence interval. Avocado plus dill plus mayo. That does sound good on sourdough. Yeah. Well, anyway, thank you for sharing that. I'll have to try that. Avocados, like, they fluctuate in price so much. I don't know why. Like, some days it'll be like an avocado is less than $1, and then the other day, other times it'll be like $1.50 an avocado. Anyway, okay. So we can make confidence intervals now. Okay. So if you recall the confidence, I mean, if you recall, of course you do. You know, we create confidence intervals for the proportion p based on a sample where we observed p hat, and the logic behind that was that we know that p hat generally stays close to the population proportion p. So when we observe a p hat, we can be confident that p is nearby. We use the exact same logic here, right? It's the same logic as, even though you can't see the invisible owner, you know the dog stays close to the invisible owner. So when you see the dog, you know the invisible owner is close by. Same idea here. We know that the sample mean x bar stays close to the population mean mu. So even though we don't know exactly where the population mean mu is, when you observe a sample and you get the sample mean is some value, you can be confident that the population mean is close by, right? And we can say we can be 95% confident that the population mean is within approximately 2 standard errors of the sample mean. And that's the logic that we use here. It's the same logic as before. The central limit theorem says, you know, x bar comes from a normal distribution. So wherever we see x bar, we can be confident that the population mean mu is close by. Okay. So basically, we can be confident that mu is between, and we're going to have x bar, which is what we observed, plus or minus basically 1.96 standard errors. Okay, and my standard error this time is sigma divided by the square root of n. So I've got x bar minus 1.96. I should write we can be 95% confident. That's a So we can be 95% confident that mu is between this and this, okay? But there's a problem. There's a problem with this, okay? And the problem is that we don't know what sigma is, right? We're trying to make a confidence interval for mu. We're saying, like, I don't know the population mean mu. I do know what my sample mean x bar is. So I want to make a guess for what mu could be, okay? I can't imagine a situation where you don't know the mean of the population, but you do know the standard deviation of the population. I mean, there might be some kind of contrived situation where this is possible, but in general, we don't know the mean of the population. We don't know the standard deviation of the population. Like, the population is too big for us to observe directly. So all we have are sample statistics. We have the sample mean, and we don't have this population mean. So there's a problem with doing this, okay? So what's our solution? Our solution, okay, sigma is unknown. Our solution is we're going to use the sample standard deviation S, right? So we don't know the population standard deviation, so I'm going to just say, all right, well, I don't know what the standard deviation of the population is, so I'm going to use the standard deviation of my sample instead, okay? So I'm going to just replace sigma with S, right? So we're going to say, let's estimate the standard error. This is the standard error. It's the population standard deviation divided by the square root of n. We're going to say, you know what, let's estimate it by replacing sigma with S, and we got S over the square root of n, okay? And this sounds like a reasonable decision, right? Like, if someone says, well, I don't know exactly what the standard deviation is, but I would guess it's something around my sample standard deviation. That sounds like a reasonable thing to do, okay? But it does introduce extra uncertainty, okay? Because we don't know if our sample standard deviation S is too big or too small. So there's extra uncertainty in here. Okay. So, so this is what I wrote. So when we use S in place of sigma, we're introducing uncertainty. Okay, we don't know if our estimate S is too big or too small compared to the population standard deviation sigma, okay? And having an S that is too small is problematic because what's going to happen is your resulting confidence interval is going to be too narrow, and that could lead you to making the wrong conclusion, right? So if your confidence interval, if you say, if the real interval should go from like say 30 to 40, but because your S is too small, and I'm exaggerating here, so if your real confidence interval should go from 30 to 40, but because of your sample, you happen to get a smaller S and your confidence interval goes from say 32 to 38 instead of 30 to 40, you're going to make the wrong conclusion, right? Someone says, do you have evidence that it's not 31? And you'd say, oh yeah, I've got evidence that it's not 31. 31's outside of my interval, so I have evidence that it's not that. But in reality, the real intervals should have gone from 30 to 40, and you would have said, oh, 31, I'm not sure. And you'd be rejecting numbers that you shouldn't be rejecting. And so, so that could lead to the wrong conclusion. So having an S that is too small could be problematic, right? So what we're going to do is we are going to intentionally make the confidence interval wider, right? So we get a confidence interval, and using our sample standard deviation S, we say, okay, it goes from 32 to 38, but we're intentionally going to inflate it. We're going to say, okay, let's basically put in like a little bit of a fudge factor and make it wider, okay? Oh, here's a good question. All right, why don't we need to apply this kind of thing, right? Because in chapter 7, we used p hat instead of p, and we didn't do any kind of adjustment thing here, right? So the answer is it's a tiny bit complicated, but because we're doing p times 1 minus p, it ends up that when you use p hat instead of p, you're right. You don't know if it's a little bit too big or a little bit too small, but it ends up balancing out, and so we don't have to worry about it too much. I know that's not like a great answer, but just kind of mathematically, it balances out, and we don't have to worry about it. But yeah, you're right. In chapter 7, we had a similar issue where we are estimating the standard error by using p hat instead of p, and you'd think, well, oh, we should have done something similar. But mathematically, when you're dealing with proportions, kind of related to the idea of you've got a p and a 1 minus p that kind of take on both sides, it balances out. So it creates less of a problem. It's a little bit more of a problem here, and that's why we have to compensate for it, okay? So what we're going to do is we're going to adjust our critical value to something a little bit larger. And so, for example, with a 95% confidence interval, instead of using a number like 1.96, we're going to adjust it and just inflate that number to something like 2.1, okay? And what number do I use? I just pulled this number 2.1 out of the air, but in reality, you're going to use numbers from something called the t-distribution, okay? And the t-distribution, it looks very much like the normal distribution, but it has what we call thicker tails. It's just kind of where 1.96 is, you just kind of stretch it out to like 2.1 or 2.2 or things like that, okay? The t-distribution has a very interesting history, and well, I don't know. We'll see if we have story time. Okay. So the t-distribution looks like a lot like the normal distribution, but it has thicker tails. Okay. And that's what we do. Okay. The size of our sample will play a role in what value we use for this confidence interval. Okay. So if your sample is very big, then the idea of using your sample standard deviation as an estimate of the population standard deviation, if your sample is big, you can expect your sample standard deviation to be a good estimate of sigma, right? Even though we don't know exactly what sigma is, because our sample is so big, we can expect our estimate to be pretty close to the real thing, okay? So, so the value that we're going to use in our confidence interval when we kind of compensate it will just be a tiny bit bigger, right? So instead of 1.96, maybe we'll use 1.99, okay? All right, so we just compensate a tiny bit. On the other hand, if your sample is small, then you have less trust in your sample standard deviation. It could be a bad estimate of the population standard deviation, right? And so we factor this in, and we kind of fudge the numbers a little bit more. And instead of 1.96, we might use a much bigger number like 2.365 or something like that, okay? So with a smaller sample, the value you use will get bigger, okay? And this is all accounted for in the t-distribution by something called the degrees of freedom, okay? Degrees of freedom, we call this df, and the df is found by taking the sample size and subtracting 1, okay? df is equal to n minus 1. Degrees of freedom is a little bit more of a complex concept as well. So, in our intro class, we touch on these things and we don't get to like delve into this. But kind of just to illustrate the concept of the degrees of freedom is like, we could play a game where I say, I can guarantee, like if we pick 10 numbers, right, I can let the class pick a bunch of numbers, and I can guarantee that the average of these numbers is going to be 100. Okay, you guys can pick any numbers you want, and I can guarantee that the average is going to be 100 as long as I get to pick one of the numbers. Okay, if I get to pick one of the numbers, I can guarantee that the average is 100. And that's easy, right? So whatever numbers everyone else picks, you guys can pick 1,000,000 or -200 or 3 or 7 or 2.8. I just pick my last number so that the sum of all 10 numbers will be 1,000. And if we get all 10 numbers to add up to 1,000, then the average of the 10 numbers will be 100, okay? So as long as I get to pick one number, I can have this guarantee that the average is some arbitrary number I pick, 100 or something, okay? And so in that case, with a sample size of 10, 9 of the numbers, n minus 1, 9 of the numbers are free to be whatever they want, and 1 is kind of locked in, right? And it's kind of related to that. That's kind of a very loose idea of the degrees of freedom. It's the idea that a bunch of these numbers are free to vary, and it kind of gets factored into this t-distribution, as far as how much it needs to compensate. And as the degrees of freedom approach infinity, the values in the t-distribution will match the z-distribution, right? And so, if you have a sample size of infinity, you would just use 1.96. Your sample's estimate of the standard deviation will equal the population standard deviation if your sample size is infinite, and you just use 1.96. You can watch these little videos. They're about like 3-5 minutes each. But here's on CCLE, where did I give you the, I forgot where, okay. So in the reference tables, this page is the t-distribution, the last page in the reference tables. And so this is kind of what your t-distribution looks like. Okay, and I just kind of cropped the top and the bottom. And so you can see in the bottom last row with degrees of freedom infinity, for confidence level 95%, we get 1.96, okay? And I don't know if you remembered any of the other values for the confidence interval, but they were values like 2.58 and 1.645 and 1.28, and these are the exact same values. So 80% is 1.28, I guess they have an extra decimal point, 1.282. 90% is 1.645, 95% 1.96, and 99% was 2.58. And so with infinity degrees of freedom, the values are the same as what we would use in the chapter 7 confidence interval for proportions. But as our degrees of freedom get smaller, okay, if we have fewer degrees of freedom, we have to kind of fudge our numbers a little bit. And instead of using 1.96, we use a slightly bigger number. So if you only have 10 degrees of freedom, so meaning you have a sample size of 11, you would use 2.28. And if you only have 2 degrees of freedom, which means you have a sample size of 3, the number you use is 4.3. Okay, so this is a lot of kind of fudging the numbers. So I'll talk a little bit about the history of the T distribution. So William Gossett was an employee of Guinness Brewery, and he was trying to basically do some quality control, assessing the quality of, I don't know, the grains that you put in Guinness beer, right? So you brew the beer with like barley and hops and whatever. And he was trying to assess this thing, and basically he wanted to use smaller samples, okay, instead of having to deal with giant samples, right? So they knew if you had big samples, you could count on the normal distribution, but if you had smaller samples, so he was trying to use smaller samples, and what was going on was that when he assumed that they were following the normal distribution, his conclusions would end up being wrong, right? So he used a small sample and they would end up being wrong because he was using basically 1.96 from the normal distribution. And they kept saying like, hey, just use the big samples. Stop trying to take shortcuts with the smaller samples. And I said, no, I'm sure you can work this out. And so, he teamed up with a mathematician and they figured it out, and they said, oh, you know what, if we use smaller samples, what we got to do is we got to compensate. And they figured out, the mathematician figured out the math, and they produced this. At the time, Guinness Brewery didn't want any of their, they didn't want the company name to be associated with potentially controversial research articles. So they had to, Gossett had to publish under a pseudonym. And so he published under the name A Student, and it became known as Student's T distribution. So anyway, you can watch these videos on your own time about it. Okay, so taking all that into account, when we make a confidence interval, we get X bar plus or minus T star, the T star coming from the value in the table, multiplied by our standard error S over the square root of n, okay? And this part, T star times S over the square root of n, is our margin of error. If we compare this to the confidence interval for P, it's P hat plus or minus Z star times our standard error, P hat times 1 minus P hat over n. And both of these confidence intervals are exactly in the form of an estimate based on the sample. We got P hat and we got X bar. And then a critical value from the table, either Z star or T star. And then we have the estimated standard error. The estimate of the standard error is P hat times 1 minus P hat over n. And here it's S over the square root of n. So there's a lot of parallels between these methods, okay? I think I'm gonna just kind of blitz through this, right? So let's assume, I was petting my dog the other day and all of this hair came off. And it's just a normal thing, right? So let's assume that, on your dog's coat of fur, the length of individual hairs are normally distributed. And let's say you obtain a sample of 10 random hairs from your dog, and the mean length of, and you decide to measure these. I don't know what you're doing, but you decide to measure how long each of these hairs are because you're interested in the average length of your dog's hair. And the mean length of your sample, let's say, is 4.2 centimeters. So I guess 42 millimeters with a standard deviation of 0.2 centimeters or 2 millimeters, okay? So we're gonna make a 95% confidence interval for the mean length of all hairs on your dog, right? So we're going to make a confidence interval for mu. That's what we want to do. Okay, so it's just a matter of plugging in the right numbers. Okay, so we've got x bar, we've got t star, and this. So we have 9 degrees of freedom, right? We've got a sample of 10 hairs. So I do n minus 1. I've got 9 degrees of freedom. With 9 degrees of freedom and looking at 95% confidence, 9 degrees of freedom, the number I'm going to use is 2.262. Okay, and so I just plug in x bar 4.2, my t star 2.262, my s, which is 0.2, and square root of n, square root of 10 here. And this becomes 4.2 plus or minus 0.143, which goes from 4.057 to 4.343. So I say I'm 95% confident that the mean length of all the hairs on our dog is between, I guess 4.057 centimeters and 4.343 centimeters. Okay. And then these are like the same conclusions that we asked. Oh, yes, viewing quiz. View quiz number 2 is the letter D. D as in dog. Oh, we're just talking about dogs, and that is the answer to our second quiz question is D as in dog. Oh, this is kind of embarrassing, but no, I'll show you. I'll show you this picture. I got this picture painted of my dog, digitally painted here. As I had him painted as if he were a general in in an army here. So this is I don't know. Okay, I thought it was cool. I thought it was so anyway, I got this. This is what my dog looks like, except now he's on a human body. So anyway, I thought this was pretty awesome. You got this. So oh, he's 13. Yeah, he's getting old. But anyway, so I have that here. Anyway, these are all the same conclusions and questions that we asked when we were dealing with a confidence interval for proportions. So we say something, do we have evidence that the mean length is different from 4? And we go, oh, 4 is not between the ends of my interval, so it's not a plausible value. We have evidence that mu is different from 4.0, okay? Do we have evidence that mu is different from 4.1? And we go, oh, 4.1 is inside the interval. It is a plausible value. We do not have evidence, or we cannot say that mu is a value different from 4.1. And do we have evidence that mu is equal to 4.2? So even though 4.2 is within our interval, our confidence interval will never say that it is exactly equal to some value, right? So these are the exact same kind of conclusions that we had when we were dealing with proportions. And then the same things, I didn't even bother putting them in the slides, but the same logic where if we want a higher level of confidence, what happens to our interval? Does it get wider or more narrow, right? So if you want a higher level of confidence, you've got to make your interval wider. And if you're okay with, if you want a smaller interval, a more narrow interval, which is generally more useful, you have to trade away confidence, or you have to take a bigger sample size. So the same kind of logic applies there. Is that all right? We're feeling good about this? I know I went through this very quickly, but I'm hoping that because we had already seen confidence intervals for proportions, we feel good about confidence intervals for means. Okay. All right. Okay, and then so now we can do hypothesis tests for mu, and I'm just going to dive in straight with an example. Okay, not even going to bother setting it up. So So we'll say, is the average length of a banana 7.5 inches? So I was eating a banana the other day. I thought, I don't know. On the internet for a while, there was like a meme where you'd put like bananas next to objects and you'd say banana for scale. But what's the average size of a banana? I don't even know, right? So somehow you get a truly random sample of 20 bananas. I don't even know if this is physically possible, logistically possible to get a truly random sample of 20 bananas. Maybe it is, but you do, and you measure the length of the bananas, and we'll say the average length is 7 inches, okay, with a standard deviation of 0.7, okay? And so we're gonna ask, does this, right, we have an average of 7 inches, and someone's claiming that the average length is 7.5 inches, does our data provide evidence that the average length is not 7.5 inches, right? So the mean is 7, and the standard deviation is 0.7. Is that evidence that it's not 7.5? Okay. So we set up our hypotheses, and we just, it's easy. Average length is 7.5. So we say mu, okay? So the important thing is you're talking about the population mean mu. Maybe I'll put that as an important. Okay, so I'll write important. We are dealing with means. The symbol hypotheses the mu, okay? So do not use X bar in the hypothesis. Okay? We don't use X bar because X bar talks about our sample, and there's no uncertainty about the sample. So okay, so we've got hypotheses about mu, and our alternative will be two-sided. We'll say that the average length is not 7.5 inches, so we say mu is not equal to 7.5. And then we pick a significance level. We'll just default to 5%, but again, you can pick a different significance level, 10%, 1%, whatever you want. Okay, and we'll check our conditions to use the central limit theorem, right? So random and independent, we're going to say we had a sample of 20 bananas that were random, so we're going to assume this condition's met. The large sample condition may or may not be met, okay? All right, so if it's unimodal and symmetric, a sample size of 20 is probably big enough, okay? But if the distribution, population distribution is skewed or really not normal, then, you know, in general, the rule of thumb is sample sizes of 25 are big enough. We're a little bit shy of that. And so maybe using the central limit theorem and approximating with a normal distribution is not appropriate, right? So it's possible that we come to the wrong conclusion and we don't even realize it because, you know, we're assuming the central limit theorem applies, but we could be wrong. So right now we're going to kind of just assume that this is met and go on, but we'll keep this in mind that this is a limitation of our kind of our work here, right? The population would be all bananas, and that's a big population, right? You know, we have 20, and you know, 20 times 10 is 200. Are there more? Is the population bigger than 200 bananas? Yes, yes, very, very much so. All right, so the p-value would be what's the probability of observing our data or something more unusual if the null hypothesis were true. So right, so our data is we have 20 bananas, X bar is 7.0 and S is 0.7. And if the null hypothesis were true, mu is 7.5, and we would expect samples where the mean is something around 7.5, okay? So what's the probability of getting a sample where X bar is 7.0 or less, or 8.0 or higher, okay? And, or, you know, what's the probability that the sample has a mean that is 0.5 inches or more away from the population, okay? Well, from the central limit theorem, we can say X bar comes from a normal distribution with a mean of 7.5, the population mean, okay? This is you plug in the value from the null hypothesis, not your sample, but plug in the value from your null hypothesis. And then, and again, we are, oh, you know what? Sorry, this is a typo. Approximated with a normal distribution, okay? But because we are estimating standard error, okay, so this will come from a t distribution. Yeah, okay. Normal distribution, but we're estimating standard error. I'll say we will use the t distribution it's fine. So we can still write this, but this standard error is we keep this in mind that this is an estimate here. So our test statistic is going to be x minus the mean divided by the standard error. Okay, we're going to have 7 minus the mean of 7.5 divided by our standard error, which was s divided by the square root of n. Okay, and we get a t value of negative 3.19. Okay, so this is our test statistic here. And so at this point, we go to our table to look up our p-value, okay? And we're going to use our t distribution with n minus 1, 19 degrees of freedom. Our sample size was 20, so we have 19 degrees of freedom. Now, using the t-table is very different from using the normal table, okay? So when you go to your t-table, it doesn't look anything like the normal distribution table, okay? So what I've done is I've kind of just cropped the top part, the headings here, and then I've just zoomed in and I've just copied this one line with 19 degrees of freedom as it, because that's the only row that really matters to us now, okay? So, so in the table, we find the row for 19 degrees of freedom, and we're going to look for our test statistic value of 3.19. Okay, so technically, our test statistic is negative 3.19, and the t-table is only positive. Okay, but it's symmetric. So what you can do is you can ignore the kind of the plus or minus signs. Okay, so we're going to look for 3.19, and we say, well, where does 3.19 fit in this kind of row of numbers? It fits in between 2.861 and 3.579. 3.19 fits in between here and here. So our value of 3.19 fits in between here and here, and what that means is that the corresponding tail area is going to be between these two numbers, 0.005 and 0.001. Is that okay? So my number is between here and here, which means the corresponding tail area is between there and there. Maybe what I'll do is I'll draw you a picture to kind of, I think a picture could be a little bit more helpful. Let me deal with that. Okay. All right. So the idea here is, so we've got this thing that looks kind of like the normal distribution, all right? And the idea is I got 0 in the middle. And here, what this table says is that, you know, if I go to, this is very much exaggerated. All right, so this is df equal to 19, degrees of freedom equal to 19. If I go to 1.328, this area here is equal to 10%, okay? And as I go further out, if I go to 2.861, this area is equal to 0.005. And as I go further out to 3.579, you know, the area, this is probably not, this area right here is going to be 0.001, okay, at 3.579, okay? And what I'm doing is I'm coming along and I'm saying, you know what, let's draw a line at 3.19, okay? How much am I shading in here? What is this area? Okay, and the answer is, I don't know. I don't know the exact area equal in that area, okay? I don't know exactly what this area is equal to. But I do know it's more than 0.001, and less than 0.005, okay? So whatever area is beyond here, we know this area is going to be more than 0.001 and less than 0.005. And that's good enough for us, okay? So we're going to say the corresponding tail, whatever it is between 0.005 and 0.001. My alternative hypothesis is two-sided, so the total p-value is going to be 2 times the tail area. So my p-value is between 2 times 0.005 and 2 times 0.001. So my p-value, whatever it is going to be between 0.01 and 0.002. Okay, 0.01 and 0.002. I don't know what the exact p-value is, but we do know it's between 0.01 and 0.002. Okay, we have a question. Is there an R function that is equivalent to the t-table? Yes, there is, okay? So you have an R function equivalent to the normal table, which is p norm, okay? And the R function for the t-table is pt, okay? So if I put in pt, you have to specify degrees of freedom. So if I say PT0 DF19, we're going to get 0.5. And if I do, so this always gives us the area to the left. So if I plug in any of these numbers, right? So if I do PT 1.328 with 19 degrees of freedom, it gives me 90%. It's saying the area to the left of 1.328 is 90%, okay? And then, so here with 19 degrees of freedom, if I type in 2.861, it's going to tell me the area to the left is 1 minus this 0.995, right? So if I do PT, what is it? 2.861 with 19 degrees of freedom, you know, I get 0.995, okay? And if I do 3.579, it's going to give me 0.999, okay, with 19 degrees of freedom. Okay, or something, you know, 0.99899, yeah, so that's 0.999, okay? And so, you know, when you use the table, you don't know exactly what it is. If I type in 3.19, R is able to tell me exactly what it is. I get 3.19, and I get 0.9976, okay? So, you know, 0.0024 would be my area. And then I would multiply that by 2. But again, it's fine that you don't know exactly what it is. You know it's between these two numbers, and that's generally good enough for us, okay? But yeah, you can use PT in R. Okay, and it depends on your degrees of freedom. Again, kind of how fat or narrow the T distribution is depends on the degrees of freedom that are kind of taken into account. Okay, so whatever my p-value is, I guess we've established that it's 0.00. Here, I'll do 1 minus this. This is what I get, and then I'm going to multiply that by 2. So my p-value would be 0.0048. Okay, so 0.0048, which is indeed between 0.01 and 0.002. But whatever it is, if my alpha is 5%, we know my p-value is less than alpha. Okay, my p-value is classified as small. And so, you know, it's technically possible to get a mean of 7.0 inches. It would be very unlikely to happen if the population mean really were 7.5, right? So if the population mean was 7.5, it's not impossible to get a sample where the mean is only 7.0, but it's very unlikely, okay? And so the fact that we actually did observe a sample where the mean is 7.0 tells us that the claim that the population mean is 7.5, it would tell us that that claim is wrong. And so we would conclude, we would reject that null hypothesis. We would reject the null hypothesis. We conclude that the mean banana length in the population is some other value that would, you know, more easily produce a sample where the mean is only 7.0. Okay, so it's more likely to be something less than 7.5 inches. And that's that. That's hypothesis testing. So we've done confidence intervals and hypothesis tests for sample means based on one sample. And then on Monday, we'll wrap up chapter 9. We'll take a look at 2 samples at a time, okay? You guys have any questions? Are we feeling okay about all of this? So question says, can you use this as evidence for a lower mean, or does the alternative have to state less than? So when we started off with this not equal sign. Okay, we started off with not equal sign, but then the fact that we rejected the null hypothesis because our sample size is 7.0 does provide evidence that the population mean is less than 7.5. So because our data came in lower than 7.5 and we rejected the null hypothesis, this does provide evidence that the mean is indeed less than 7.5. So yes. Oh, third quiz answer. Thank you. Thank you for reminding me. Third quiz answer is A as in apple. A as in apple will be the last quiz answer. Third quiz answer, A as in apple. All right, we'll call it a day here. We'll wrap it up here. If you haven't read the article, please make sure you read it before your discussion section. I know some of you have discussion section in like 15 minutes here, so you know, make sure you read your article, and you can start taking a look at the article questions, but you guys will go over them in discussion there. Okay. That's all. Have a good rest of your week, and we will see you guys next Monday.